Hi, I'm Damien Hilloulin. I work at Oracle Labs in the PGX group, working on graph and graph machining. Today, I'm going to present to you the session about learning on graphs with exponential graph neural networks, which is centered around graph and graph machining techniques. As for the content of this presentation, first I'm going to explain a bit what tools you can use, what services you can use so that you can actually use graph and graph machining with Oracle products. In a second part, I will describe more what graphs we can use and what GraphML techniques we can leverage to extract more information from those graphs. After that, I will detail more of real-life GraphML applications. And at the end, we will just see how to continue your graph journey, looking at more Oracle CloudWorld presentations or using the tools available with Oracle. So let's start with graphs and graph at Oracle. So PGX, the group I work in, is making the PGX component delivered in several Oracle products. And PGX includes several parts, including the graph machining part, of course, but also a graph query language so that you can query the graph itself with a language close to SQL. And it includes also analytical algorithms, such as the traditional PageRank or Bellman-Ford algorithms used for various more traditional tasks. PGX is designed to scale on very large graphs from what we call small graphs with millions of vertices and tens of millions of edges, up to industrial scale graph with billions of vertices and tens of billions of edges. PGX is integrated in different Oracle products. And if you want to actually try some of the things we will discuss today, maybe the easiest for you is to use some of our cloud services that include the GraphML technology. The most featureful is probably the OCI Autonomous Database Graph Studio. There you will be able to leverage all the PGX functionality, including the graph querying, the graph visualization, and the GraphML features. In the OCI data science service, you will be able to leverage the PyPGX Conda environment to run some of your GraphML applications. There you will not have some of the features from the Graph Studio, such as the graph visualization or the graph querying, but it should get you started pretty quickly, especially for people with a machine learning background. All right, now let's see what graphs and GraphML can do for you. So starting from graphs, graph can represent everything. It's a data model similar to how maybe like the relational data model can store data. In graph, we can represent every kind of data. But the great advantage of graphs is that actually we can connect very different data in a way that is very visualizable and for which actually the algorithms or machining techniques can leverage extra information. Here on the screen, we have actually a representation of a financial graph. It's an example graph, not real data, but it gives the idea of what we can see in big industrial scale graph. So at the center, we have what represents an entity. So an entity can have several accounts and connected to different people that owns those accounts. And the accounts can be used to do money transfers, and an entity can perform such transfers in different manners. So as you can see, this graph represents a lot of different kind of data. We have different types of vertices, so the little circles here, and we have different type of edges connecting them all. What we support in PGX is this kind of heterogeneous graphs where we can have different types of vertices, different types of edges, and we can assign different properties to both the vertices and the edges, and these properties can differ per type. So let's say, for example, here, if we look at the people such as Robert Finch and James Ellis, they might have attributes such as a date of birth or a surname and first name and so on, while the accounts will have probably an ID, a balance, and a date of creation. And the edges, such as a cash withdrawal, will have a timestamp, an amount that was transferred, while the edges between a place and a person might not have that many properties. So this is a kind of graphs we can support. And with that, we can do graph machine learning. So starting from the raw data, which might actually look like normal tabular data, we make the graph. So that's where we connect the things. We indicate, oh, this is a vertex, this is an edge. After that point, we can apply graph machining technique to extract information from that. The output of most of the graph machining techniques are representations of the vertices with n-dimensional arrays of numbers, or we can also have models where we directly do classification or supervised tasks. So what the graph ML technique will do is actually leverage the topology information, so how the vertices and edges are connected and form a single graph, and also the attributes, so the features that might be linked to those vertices and edges. The power of GraphML comes mainly from the fact that you don't have isolated entities, you don't have just a vertex where you look at to only make this prediction, but you look all around the vertex, how it's connected, and the information propagates in that graph. Which is why on many tasks where we leverage GraphML, we can achieve better accuracy or better performance in general than more traditional techniques. As for what we have in PGX, we have various models. Some of them are used to generate embeddings for vertices. So for example, deep work is a method that will learn embeddings, so n-dimensional arrays of numbers for each single vertex in the graph. This deep work technique just looks at the topology. It doesn't look at the features. So for problems where features might be very powerful to indicate the signal for the end task, it might not be the best method. PG2VEC is another model that we have where we learned embeddings again for graphlets, so little subgraphs, and it leverages mainly the topology, but a bit the features. What we introduced most recently is the GraphWise model, and this is our strongest model, of course. So with the GraphWise model, in contrast to deep work and PG2VEC, where we learn a vertex we learn an embedding per vertex or per graphlet. With GraphWise, we learn a function to generate such embeddings, such that it can generalize beyond the graph it was used during the training phase. And with this generation function, actually, we take into account the topology again, of course, and the vertex and edge features. We have different variants of this GraphWise model. So we have supervised versions, so that if you have actually labels, for example, for a classification task where maybe you want to classify if a vertex is a fraudster or not, if you have those labels indicating that in your data, you can use the supervised model. But in the case where you might not have the labels, or you actually might not know exactly what you want to use the model for in the end, you can still use the unsupervised variants to learn to generate good embeddings with GraphWise, and then use those embeddings in a downstream model later on. The great benefit of GraphWise is that it's explainable, meaning that we will be able to produce an explanation of what mattered to do a given prediction. And this explanation, as we will see, is a graph itself, so it's very convenient for us. Let's dive a bit more into the GraphWise approach. So the GraphWise approach is actually based on some publication in academia, the GraphSage model from Hamilton and others. And this approach was very important. It gave a great recipe for how to make scalable models that can be applied on very large graphs and still have very good accuracies and performance speed. And to do so, to solve both the problem of scalability and accuracy, GraphSage uses an approach which it can be divided in 3 steps. So here, the first step to make the prediction is to start from the vertex of interest, so the vertex for which we want to either make a prediction or generate a final embedding. So here on the figure. It's the dark vertex in the center. And from that vertex, we'll explore the graph, not completely, not exhaustively, but we will sample vertices around it, traversing some edges. So the first circle around that center vertex are the vertices that might be reached by following one edge. The ones with the light shade of blue are the ones that are selected with sampling, while the one that was white is actually not sampled. And from those sampled vertices in the first hop, we can do again the same operation and sample vertices with a second hop. So after we have sampled this subgraph centered around the vertex of interest, that's where, let's say, the math starts and where the machine learning really begins. So we talked about how the graph machine learning techniques propagate information. Here with GraphSage, this propagation of information starts from the most outwards vertices that were sampled during the first phase. So here we start from the vertices at hop 2, and we will propagate their features transformed with some mathematical transformations towards the vertices of the first hop, so sampled at the first hop. And again, we will repeat this aggregation and propagate that information to the center vertex. So that's where the information propagation happens. And basically, the information propagates within those two hops. Of course, we can configure that here. It was an example to say 2 hops, but in practice, you can configure as many hops as you want or as you need. And the third step, so we have aggregated all this information. We can have more computations happening on all this aggregation information to do the final prediction. If we look at how the model looks like more precisely, it can look as followed, as shown on the right-hand side. So contrary to more, let's say, traditional machine learning models, the architecture is not just a straightforward line from top layer to bottom layer. We have actually information flowing in both directions. Here we represented the fact that starting from hop 0, so the center vertex, we need first to sample the neighbors, and then again the second hop neighbors before we actually start doing computations. So we compute from second hop layer back to hop 1 layer, and then hop 0 layer to finally go to the prediction layers. So here, everything is pretty flexible. With PGX, you can configure how many neighbors you sample at each stage, what kind of layers you want to use every time, what kind of hidden embedding size you need between different layers. But more critically, you can change what happens in the prediction layers. So we have different loss functions that are tuned for different use cases or different tasks. So of course, you can use the more traditional loss functions such as softmax cross entropy if you want to do classification or multi-class classification. But we have DevNet loss, for example, tuned for more anomaly detection use cases where it's semi-supervised, and it will also take into consideration that in anomaly detection, you might not have labels for all the anomalous case, but actually just a few. So that's tuned for this kind of use cases. And for the unsupervised training, so when you don't have labels, at the moment we have a loss function based on the deep graph infomax loss, which will make it possible to learn high quality embeddings in this unsupervised training setting. So let's look at the explainability. We have this graph-wise model where, yes, we can make predictions based on the neighborhood. And when it happens during inference, basically we sample this neighborhood, we aggregated information from the outward layers back to the center. But how can we explain what was important or not? That's where the GNN explainer technique can help us explain the prediction. So what it does is that it can assign scores to the different vertices in the sample subgraphs. And if the score is 0, it means if the vertex was not sampled, it wouldn't have changed the prediction. But it goes to 1, it means it was critical to the explanation. And we can have also scores for the different properties. So here represented with different boxes on the right-hand side of the picture. We can clearly see what were the features that contributed to the prediction. And we summarize that in a global object saying what features were globally important for that prediction or not. Explanation produced by these methods are graphs themselves, so that can be visualized. And it's very nice, for example, to actually use it in different use cases where it might be necessary for regulatory reasons to explain why the prediction was like so. So, for example, in Europe, there is a GDPR laws that require an explanation capability for example, in the banking sector. So that could be a way to start generating an explanation. Of course, it might require more post-processing, maybe to make some text out of it so that end users can understand it. But it's already a good start to see what was influencing the model. Explanations can be used to also beyond just regulatory use cases where maybe we want to be able to take action from a prediction of a model. Sometimes we still need humans in the loop to be able to, from the prediction of the model, do the necessary next steps. Here it can help the people to actually understand what next step they should take. And in general, it can also help to increase the confidence in the model, either at the development stage of the model, for example, to be sure that the model learned something that makes sense, or in production to also look back and be sure that it's generalizing well. All right, so we looked into the techniques that power graph ML. Let's look at some brief applications. So we can apply graph ML techniques in many types of scenarios, many kinds of data. Here we have this use case around the cybersecurity kind of domain. We have a dedicated talk at the CloudWorld 22, so you can check that out if you're interested more into this specific use case. But basically, in the context of a cloud infrastructure such as OCI, we want to guarantee security of the machines, meaning we want to be able to detect if attacks are going on specific machines, or if maybe there is anomalous behavior on some machines. And to do so, we, behind the scene, monitor everything happening on the machines. So we can capture information such as the different system calls, file accesses, network activity that happen on that machine. And while it looks like maybe a more temporal kind of data, we can actually make a graph out of it. We can capture the interactions between processes and different files and so on, or system calls to model that as a graph. And there, to do the final detection, anomaly or not, we use a GraphML model based on GraphWise with DevNet, tuned for anomaly detection. The graph model is a very precise one, so it actually takes a bit of time. Maybe it's a bit too slow for using it on all the logs, so we pre-filter with another model before. And we use the results of the GraphML model to actually continue the investigation when there is something to investigate. And we can use for that the embeddings generated by the model to look for similar previous use cases or look compared to reference attacks. And after these predictions are made, we can investigate with a very visual workflow. We can see what mattered for predictions. We can see explanations. Actually, we generate text explanations out of the GNN explainer graph we get. and it makes a very good workflow for investigators. Another use case, again, that we present at this CloudWorld is around healthcare and cybersecurity. So we mix both into this presentation. In healthcare, again, data might be thought about like time discrete kind of events, but actually when we turn it into a graph, we can achieve much better results. And using the GraphML techniques can boost results in use cases such as predicting the relationships between patients and diagnosis, and it can be quite helpful there. So again, it's one use case where maybe the data didn't look like a graph at the beginning, but turning it into a graph actually made a difference and improved the accuracy. And in this same presentation, we show actually also another part where we use a deep work model, so different from the GraphWise model. For people interested in this specific model, it could be a good presentation to check. With this model, we can learn embedding, and we can do embedding similarity search to find relevant clinical trials for a given patient. All right, we looked briefly at some applications. Let's see what we can do next. So first, I encourage you maybe to check more of our CloudWorld talks. I presented a few slides of the and the one dedicated to cybersecurity, but we have more around also the financial domain, so you can check that one out if you're interested. There's a big focus on the financial crime detection. And there's another talk also around how GraphML is being used to do ad fraud detection with some real life examples of how we caught some ad fraud bots using those GraphML techniques. All right, I'm reaching now the summary. So I hope I convinced you that graphs and ML are more powerful together. Graph is a very good data model to represent any kind of data. You can connect different entities with relationships as edges. And by modeling this as a graph, you can extract the relationships that matter for your machining task. They're dedicated graph machining models that leverage all this information in the graph. They look around, use the topology, they use the features on both the vertex and the edges. They work on any kind of graphs with heterogeneous graph with different types of vertices and edges. And those graphs, even the models are more complicated, they are more powerful, but still explainable. As we saw during this talk, all the predictions of the GraphWise model can be explained with a graph itself, which makes it for very convenient visualization and for very actionable predictions. If you want to try all this out, you can leverage maybe some of our cloud services. It will be very easy for you to try everything in the ADB Graph service. Also, if you are more machine learning oriented, the data science service might be the most convenient for you. So you can try that one out with the PyPGX Conda environment. With that, I reach the end of my presentation. I would be very happy to hear about you. If you have any question around graphs or graph machine learning, feel free to send me an email to my here indicated Oracle email address. And we will be very happy to help you start your journey with graphs and GraphML. Thank you.